Uh, Welcome everyone for my presentation. Boosting Group Journal Clubs. This journal club is based on the article A Spin-Orbit Torque Device for Sensing Three-Dimensional Magnetic Fields. It's Longue et al. And it's published in Nature Electronics. I will start discussing the goal of this study by mentioning a few forewords. First of them is about magnetoresistive sensing, since sensors and sensing mechanisms is quite crucial for industry, and there are lots of investments in this subject. There are lots of physical mechanisms that can be used as a sensor. And by the improving magnetic technologies, magnetic elements have obtained a very crucial place in this advancement of sensor technologies. So magnetoresistive sensing is amongst these technologies, and one of the most important physical mechanisms and physical phenomena opened the doors for this improvement are basically Hall effect sensor, anisotropic magnetoresistance sensor, giant magnetoresistance sensor, and tunneling magnetoresistance sensor. These physical mechanisms are quite familiar for us because they are at the basis of spintronics. They are fundamental physical mechanisms in spintronics, and we are familiar with their usage on the memory applications. But now we are also observing their usage and their utilities on sensor technologies. At the Hall effect sensor, it's basically the classical Hall effect, applied magnetic field and passing current into the material, and charges are separated, and there's a Hall voltage to be read on the voltmeter. And anisotropic magnetoresistance, as we know it, it's the relationship between the angle between current and magnetic field, applied magnetic field. And by changing the magnetization of the sample, we can also create the resistance change, which causes the change of the parameters in the sensor. And then giant magnetoresistance and tunneling magnetoresistance mechanisms are also applied to these sensing mechanisms and created new technologies on them. But it was simply not enough for 3D magnetic sensing, magnetic field sensing, because when you work with these technologies, one needs to create each setup, each experimental setup for three different dimensions. And magnetic field is at X direction, at Y direction, at Z direction. So you need to understand the three distinct dimensions and create three separate experimental setup for all vectoral positions. So this would be a problem for commercial use. If you want to make a huge processes and use this technology in the commercial use, there must be a change and there must be an improvement for this lack of utility. So here comes the spin-orbit torque. Spin-orbit torque is a very familiar technology to us that we are actually using to count the magnetization of a layer by using the spin-orbit interaction of materials. And as you can see, there are the torques being applied to the magnetization of the ferromagnetic layer in this context. And we know that these changes can also be done by spin-orbit torque with advancing spintronics technology, not only by the physical mechanisms that I mentioned before. So in recent studies, we know that using a ferromagnetic layer and a heavy metal layer is an ordinary way to obtain spin-orbit torque and switch the magnetization of the ferromagnetic layer by using spin Hall effect or Rush-Beidel-Stein effect, which means that converting the electrical charge current into spin current and obtain this obtain the magnetization change in the ferromagnetic layer. And by this magnetization change, we can also pass directly to the resistance change, which means the parameters of the sensor is changing. So we can actually create the logical bounds between switching magnetization by spin orbit torque and its usage on the sensing technology. So the papers basically says, why don't we use this technology and create a 3D magnetic field sensing method? So in this methodology, we have two very important phenomena being used, and this is crucial for the understanding the mechanism of how the device works. So one of them is the anomalous Hall effect, and one of them is the spin Hall effect. At the anomalous Hall effect, it's basically Hall effect, but instead of the applied external field, we have the magnetization of the material. And there goes the charges, as you can see as the green dots. There goes the charges with magnetic spins, and they are separated due to their spins, but it's not homogeneous. And there's a voltage difference created in a voltmeter, which causes the whole potential read from the voltmeter. And as the spin Hall effect, as you can see, there's no magnetization or no external magnetic field applied, but the material, by using its spin orbit coupling, spin orbit interaction properties, material makes the distinction between the up spins and down spins. So we have the pure spin current polarized inside the material, and we can inject this pure spin current into the ferromagnetic layer on top of the material. So this is how it basically looks like by using the spin orbit torque. And if you have a ferromagnetic material with domain walls, this is also possible to move these domain walls, put them into a motion, and create the magnetization switching, and so the resistance change by using the spin orbit torque. Nothing more but the spin orbit torque with a heavy metal layer on under the material you want to switch. So in this study, domain wall motion have been obtained by two physical mechanisms. One of them is the SOT, and one of them is the external magnetic field applied in the out of plane. And when they want to achieve the SOT domain wall motion driven by the SOT, they use the in-plane field, in-plane applied field, and in-plane current injected into the system. And a mathematical realization of this SOT, as you can see given below. And I don't deal with formulas, or I don't want to explain anything mathematically. The reason I put this formula on the presentation was for you to see what SOT depends on the mechanism. As you can see, there's the magnetization, there's the spin Hall angle, there's the current density. So these are the parameters that determines the effect, and how we can use these parameters to enhance and create a better system in the future, maybe. So let's get back to the original paper. This is the sample device they are using, and it's Tantal 10 nanometer, Coffee B 1.2 nanometers, MGO 1.6 nanometers, and Tantal 20 nanometers at the top. As you can see, this device is designed for sensing three-dimensional magnetic fields, which can be in three distinct vector ways. Hence, the ultimate goal was to obtain this sensing mechanism by using only one device. So the nature of SOT is quite feasible for this, because we know that geometrical aspects affect the SOT, and we can observe SOT is enhancing and descending in some of the anisotropic effects. So they started with injecting the current at Jx at the x direction. So as you can see, there's three different cases in here. One, Hx is parallel with Jx, and they observe the SOT with domain wall motion. And by the way, the voltage you read is actually the anomalous Hall effect I mentioned before. They read the anomalous Hall resistance values. And at the second one, you see no domain wall propagation. And at the third one, there is a domain wall propagation, but this is not driven by the SOT. So what's this, where this idea comes from? Here are the example data that caused them to think of the physical mechanisms behind the domain wall motion. So when we check the first graph, it says that there are two current scanning from not current scan. It's the constant current, but the magnetic field scanning. One is at 6.8 and other is minus 6.8 ampere over centimeter, milliampere over centimeter square. And this is the current density. Since, as I mentioned at the last slide, the physical properties of the system depends on the current density. SOT highly depends on the current density. So as you can see, the behavior here and behavior at the third graph are totally different. One mimics the other, and at the other side, it's anti-symmetric. How can we make a comment on this when we think? Red point starts from something around 600 milliohms, minus 600 milliohms, and grows back to 600 milliohms. But when we switch the currents in the other way, we observe exactly opposite behavior. So this gives the idea that it looks like spin orbit torque behavior. I think I had a communication problem. Okay, now I go on. Where was I? Oh, okay, I think it was here. Okay, and this looks like the spin orbit torque behavior. And when we see the third graph, where the Hz is orthogonal to Jx applied current, as you can see here, they are exactly the same. It's not same with the first behavior, and they are not symmetric. They are exactly the same behavior, regardless where the scan comes from, where the current is scanned. It doesn't matter. Even if you go from plus to minus or minus to plus, it has the same behavior. So it looks basically like how a domain wall moves by the influence of an applied external field. When we look at the HY, we see that no anomalous Hall resistance is obtained, which means that there is no domain wall movement, and the effect, this physical mechanism has no effect on this structure. So in the second case, to make sure that their ideas on isotropic property of this spin orbit torque and domain wall movement is correct, they also tried to inject the current from Jy. So the sample structure is basically symmetric, and it doesn't matter where you inject. You have all the same current density anyway. So it will be a problem for them. They just had to change the voltage reading property, So they just go on with that. So in that configuration, we see that this time, no domain wall propagation when we apply the magnetic field from X direction. And when we apply the magnetic field from Y direction, we observe the SOT drives or SOT driven domain wall propagation. And it just like the last experiment, HZ drives the domain walls and causes the resistance change in the third configuration. So here are the data for that. As you can see, there's no expected resistance change in the X direction, magnetic field scanning, and SOT behavior is expected to be achieved in the parallel configuration of applied external field and injected current. And the same behavior with JX injected current is also obtained by using orthogonal symmetry. So after they analyzed their data, they found out the relations for change of magnetic field to change of resistance. So they created the mathematical relations between them and their injected current densities. So here are the line fittings for these values, for these parameters. And this is basically the sensitivity of the experiment. So how much resistance do we have changing when we apply amount of magnetic field change? So this will actually describe the sensitivity of your sensor. How small magnetic fields can you measure and how reactive your sensor is? Because if you have a good sensor, you need to obtain a change in the sensor even in the smallest amount of magnetic field changes. So they did it at the three distinct coordinates, three distinct vector systems. And this means that X and Y direction has nearly the same sensitivity, but Z has a greater sensitivity. And this is the noise spectral density of this device to compare it with nearly commercial devices that being used in the industry. As they gave the data, they are close and better from the commercial magnetic field sensors, which are done by TMR and GMR effects. And this is the performance analysis. As you can see here, X and Y axis is basically works between 10 Ørsted and minus 10 Ørsted. But Z axis works between 4 Ørsted and minus 4 Ørsted. So sensitivity for Z axis is quite different from X and Y. And this is the noise density for 1 Hertz of change and linearity error analysis and its resolution. So at the end of this, they by using magnetization, they obtain the switch by using SOT and OP field, domain wall motion. New type of magnetoresistive sensor can be used for three-dimensional magnetic field sensing. So they actually obtain the change of this resistance in 3 different dimensions, and they have all sensitivity data. They have performance for the sensor. So it is qualified that this magnetic field sensor can sense the 3-dimensional magnetic field by using only one single device, by using the structure of SOT and enhancing it with out-of-plane applied field. Unlike other magnetoresistive sensing technologies, 3 different components of magnetic field vectors are sensed by using one single device, thanks to isotropic nature of SOT. Comparing TMR and GMR device, devices, noise ratio is also lower and more applicable into industry. Thank you for listening. Waiting for your questions.